Thank you for the invitation. Today I will talk about how I worked on the Strange Duality conjecture. This is my PhD project, and I really hope that I would post the paper this week, but there were some inconsistencies with multiplying 2x2 matrices in the appendix, so I guess I will have to double check it. But this talk will be about the easy part, so like almost no matrices. As for the conventions, I usually assume that all functors are derived, except I distinguish between home and R-home because I want to consider home in the derived category. The field is algebraically closed at characteristic 0. And when we have a stack X, we can consider various flavors of K-theory. So we can consider algebraic K-theory, K0 X, which is the Crotontic group of perfect complexes on X. Whenever this makes sense, so like X is Noetherian. And we can consider the topological K-theory on X. It recovers topological K-theory for the case of complex varieties. But more generally, for example, for stacks or for stable linear categories, it was defined by blank over C and by Carchedi. I'm not sure how to read the name, Carchedi El Manto, over an arbitrary field. And when we consider a complex variety, we can talk about the oriented topological K-theory. So it is, taking a topological vector and fixing its determinant. Okay, that's for conventions. And let me talk a bit about how this started. So I first attempted to strengthen the results on the Strange Duality, and this was largely motivated by the work of Alina Marian and Dragos Oprea. The Strange Duality is a conjectural duality between global sections of certain natural line bundles on moduli spaces. So for the more classical formulation is we take a smooth projective complex variety. We fix a quasipolarization. So polarization means a choice of an ample line bundle. And if I say quasi, it means that line bundle is only big and nef. And for a fixed choice of a K-theory vector, algebraic K-theory vector, I can consider the moduli space of stable sheaves on X with respect to the quasipolarization H, which have class V in topological or oriented topological K-theory. The Grothendieck group has a natural pairing called Euler Pairing. Phi of V and W is defined as the Euler characteristic of the derived homomorphisms from V to W. So instead of V and W, take any sheaves that represent this class and take Euler characteristic of their home. For the formulation of the strange duality, I want to switch to the symmetric Euler pairing. Which I define as chi of V tensor W. So I can view it as chi from V dual to W, or as the Euler characteristic of cohomology of their derived tensor product. Then we want to construct the strange duality morphism.
Sorry, can I just ask you to repeat something?
Yes.
So V tensor W, you said you pick sheaves, you pick any sheaves representing V and W?
Yes.
And it doesn't matter which ones you pick?
No, as long as the tensor product is derived.
Okay, thanks.
Yeah, the number that we get is always the same. So for the construction, we pick two orthogonal vectors. Enter W is equal to 0. Then assume that both spaces of stable sheaves have a universal sheaf. So for example, we take MW cross X, and it should have a sheaf such that for each point of MW, the restriction of E on this point cross X represents the stable sheaf, is isomorphic to the stable sheaf represented by this point. And I consider two projections, P1 and P2. Then as the first step, for V in the algebraic theory that we chose here, I define the theta line bundle as the determinant of the derived push forward with respect to P1 of E derived tensor P2 upper star V. And this will be a sheaf on W. So again, I want to say that V was taken in the algebraic theory. So it makes sense to take its push forward, to take its pullback and push forward, and then consider the determinant of this algebraic theory class. And this will define a unique line bundle on MW. And similarly, we define theta W, a line bundle on MV. Is the construction of the theta line bundles clear? Then I want to define a certain locus of pairs of sheaves, MV and cross MW. It is the locus of jumping zeroth cohomology. So sometimes this locus is a divisor if it happens when H0 is generically 0. So we make an additional assumption that D is a divisor in the product. Then in this case, people can prove that of D, the line bundle corresponding to D is isomorphic to the outer product of, to the box product of theta W and theta V. And therefore, from of D, so D was a geometric locus, so it defines a section S up to a scalar. And it means that we have a section of theta W box product theta V on the product of moduli spaces. And then by Gunner's formula, this is isomorphic to H0 of theta W on MV, tensor H0 of theta V on MW. And by linear algebraic version of tensor homogeneity, we say that we have a morphism from the dual of the sections of theta W to the global sections of theta V. This morphism is denoted by D, and it is called the Strange Duality morphism. And the main question of strange duality is when is D an isomorphism? Somehow this whole business started from representation theory of affine Lie algebras and this level rank duality, which was called a strange duality by Frankel. But I don't really understand this part, so I will tell you a brief recap of the history that I do understand. Namely, the strange duality holds for X when X is a curve in full generality. So they started with the work of Bourvil, Pantev, and Donagin giving some first glimpses into why this may be true, and then Vilcali, Marianne, and Opria proved this in whole generality. It was cool. It was also proved for some surfaces And like giving a historical overview for surfaces is very scary for me because there is a lot of work on this, and it really is like this big scary zoo of strange dualities for surfaces. And an interesting setting was suggested by Alina, Marian, and Dragos Oprea. They started considering the strange duality in the relative setting. So instead of studying strange duality over one surface, they studied the strange duality over a family of surfaces. So we switch points for moduli spaces of surfaces. We switch moduli spaces for relative moduli spaces. And in this setting, one result that I have been working on is the generic strange duality for K3 surfaces. They proved this result for a collection of pairs of vectors for K3 surfaces of degree at least 4. And as for degree 2, there was a technical problem that I worked on in the last year, so which was that we needed to work over the quasipolarized locus. We need to define relative moduli spaces over the quasi-polarized locus. So the polarization H is no longer ample, but instead big and left.
Can I ask a question?
Yes.
So when you started this section, you said that we pick V and W to be orthogonal with respect to the pairing.
Yes.
Is there some intuition for, I mean, is that required for stuff below to make sense? And is there intuition for kind of what that means?
I don't see intuition in the pointwise setting. So I don't see intuition here, but it will be vital for constructions to make sense in the relative setting because this orthogonality condition will kill twists that inevitably arise when I construct even theta line bundles.
Okay, thanks.
So can I ask something? You don't need it so that the D is a divisor. That is not hidden in orthogonality, in the fact that the locus where the H0 jumps is codimension 1.
So Alina said in the chat that it is necessary for constructing determinant line bundles.
Ah, yeah.
And just to be clear, the D being a divisor, that's an assumption, right?
Yes.
It's an assumption on V and W.
Yes. And in order to prove the strange duality conjecture, one needs, as a step, one needs to prove that D is a divisor or, yes.
So actually just one thing, so it's expected to be a divisor, but it might not be, but actually it is a divisorial locus. So the expected codimension is 1. Now you have to check that it actually is. That's what Svetlana is saying, right? I mean, so yeah. And the orthogonality is crucial for that, you know, for both to define the determinant line bundles and to have this expected locus to be to have codimension 1. So now if it actually is, it's a question of the actual geometry. So that's what she's, yeah, that's what Svetlana was. Sorry.
Thank you. Are there any other questions on the construction? If not, I would like to go on. And I said that for degree 2, we need to work over the quasipolarized locus. And stepping away from the ample locus requires us to retrace all many classical results of the moduli theory and use the heavyweight machinery of good moduli spaces in order to construct relative moduli spaces. So in order to glue the moduli spaces of the quasipolarized locus into the relative step. And the main result that I want to describe today is the following. So let's K be a moduli stack of quasi-polarized K3 surfaces. Let X be the universal K3 surface. With the universal quasi-polarization H. And consider a topological K-theory vector B on X. And assume that for V, pointwise on K, which means for every K3 surface with the quasi-polarization H inside K. H semi-stable sheaves are stable. So this is a crucial assumption of stability and semi-stability being equivalent. Then I prove that the stack Q is the stack of H stable sheaves of topological K-theory class B is algebraic. And I want to note that for every particular K3 surface, the restriction of Q to this surface is stacking, because I don't want to forget the automorphisms. And second, there is a good moduli space M due to M, such that M is a step, but over each point of K, it is the moduli scheme of stable sheaves. And in the next part, I will describe the outline of this construction. I'm going to define good morphisms and good moduli spaces later. Besides this, are there any questions about the formulation? Okay. So let us talk about the relative moduli instead. So let X be the universal surface and K is the stack of surfaces. Then first, consider the stack of flat families of sheaves of a fixed numerical characteristic. Then, for example, by the result of Lively, this thing is an Artin stack. And there is an older work of Artin that also works with the flat families of sheaves, but I cannot give a precise reference. But I can give a reference to Lively's paper. I think it is really cool. And then we can consider the substack of stable sheaves. It is the subfunctor of stable sheaves. I prove that it is open in M tilde, therefore it is also an Artin stack. And the proof requires some point set topology and Noetherian approximation. And this is all pretty formal, and I wouldn't like to go into too much details. And instead, I would like to show how good moduli spaces work and what they are. And I will start with the definition of good morphisms. This definition was first suggested by Alper, and then there was a lot of work on this by Alper, Einloth, Halpern, Meissner, Hall, Reed, Halpern, Meissner, Reed. And like this whole thing has been my favorite business in the last year, that I learned in the last year. So let me define what this is. A quasi-compact morphism of algebraic stacks It is called good. If the non-derived push-forward functor is exact. And shockingly, it is not equivalent to vanishing of higher derived functors because of some sticky business. And the second assumption is that the natural morphism from the structure sheaf to the push forward of the structure sheaf is an isomorphism. And in the case when Y is an algebraic space, then the above thing is called a good moduli space. Alper calls the morphism, the good morphism between steps a good moduli space morphism, but I think it is too long, so I contracted it to just good. And so there is some GRT ideology behind the definition of good moduli spaces. Namely, it is the invariant or the stacky formulation of good quotient from the GIT, and for me the purpose was to make the relative steps less stacky. Okay, so why are good morphisms good? So for example, we have a descent lemma that I proved along the way. Quasi-coherent sheaves satisfy descent along good morphisms. And for the proof, if we have f from x to y, then that Q co-satisfies descent means that the category of descent data on x, so it is sheaves on x within isomorphism when they are pulled back to x cross y and y cross x, that satisfies co-cycle condition. The category of descent data is equivalent to the category of quasi-coherent sheaves on y. And I find the proof really cute because it is formal and done in 2 steps. The first one is showing that abelian pullback is fully faithful. And the non-direct push forward detects 0 objects. And for both of these steps are direct application of the definition and some general properties like projection formula that's Alper proved for good morphisms. And these two formally imply that they are defined in equivalence. Are there any questions about the definition of good moduli spaces?
Yeah, could you repeat the second part? Sorry, the good moduli space.
The second?
Yeah, in the definition. Yeah.
Yes. So we say that a morphism of algebraic stacks is good if it satisfies these two conditions, and if we have such a good morphism f from x to y, and y is an algebraic space, then y is called the good moduli space of x.
Okay, thanks. Alina suggests an example. If you maybe it's a good to add if you have one.
The next section would be one kind of example, I guess. But for simpler examples, one can, like good quotients would be good moduli spaces, or identity morphism is a good morphism. And if I take over a variety x, I take the moduli space of stable sheaves. And if I take the moduli step of stable sheaves, then the natural morphism is a good morphism. And the purpose, the goal of the next, I guess, 5 or 10 minutes of the talk is to make this example relative. To construct relative good moduli spaces.
Can I ask a quick question?
Uh-huh.
It's in the same vein. Is suppose you have like an affine variety with a group acting on it,
Uh-huh.
then you can take the stack quotient,
Uh-huh.
and you can also just take the spec of the invariant subring.
Yes.
And I think there's a map from the stack to the affine quotient. And do you know if is that a good moduli space? Is that like a model for what we should be thinking of?
Yes, I think that this should be a model to keep in mind.
I usually think about finite groups, so I don't know if maybe this is all trivial for finite groups or something like that. Yeah. Anyway, I didn't want to hold you up, so you can just go on.
Yeah, I'm sorry.
That's fine.
So let Q be, let K be a stack of quasipolarized surfaces. And Q is a relative moduli stack of stable sheaves. So I already showed that this is an argent stack. Then a lemma if K is a Noetherian scheme with a morphism to the stack K. Then we can consider this pullback diagram QK goes to Q, goes to K, and QK is the pullback of Q along the chosen morphism from a scheme. Then QK admits a good moduli space. QK goes to MK. This is relative to the scheme K. For the proof, I use the work of Alper-Heinloth and Halpern-Leisner, the paper where they prove a criterion for existence of good moduli spaces. And it requires checking several technical conditions, which is doable, and they ensure that MK exists for this QK. And I say that these MKs can be good for all choices of a scheme K into a relative good moduli space. So there exists a good morphism from Q to M relative to K, such that M is an algebraic stack. For every K from a Noetherian scheme, the pullback of the constructed stack is isomorphic to the good moduli space. And this morphism is good. The proof is done by gluing argument. So since A is an arching stack, I can choose a smooth surjection so like I want K to be an arching stack of finite type so that I have a smooth surjection from a Noetherian scheme. And for this phi-lemma, I have a good moduli space. Then I use universality of good moduli spaces to define that we have the following sheaf diagram, but it is two-level because we are working with stacks, which are sheaves with values and quotes. And we define M to be the gluing of this diagram. That is, we take the co-limit in the category of stacks. And for algebraicity, we recall that we have a smooth surjection from K to K. Therefore, when we pull back from to get MK, we get another smooth surjection. And by universality, MK is isomorphic to the MK constructed in this lemma, which is an algebraic space. Therefore, it admits a tal surjection from a scheme. And by composing the morphism U goes to MK goes to K, we get a smooth surjection onto oops. Okay. Sorry, this should be script M. By composing U goes to MK goes to M, we get a smooth surjection onto M from a scheme, which shows that the stack is algebraic. Any questions about the construction?
So yeah, I have a question. Like, how just to develop a little bit of intuition. So what is it missing here to have a coarse moduli space, a variety? You know, I don't. I know it's a vague question, but you know, I want, because I don't know, some right stable maps to relative right K3 surface. If you put them in a family, such a thing has a coarse moduli space, right? And I guess this whole story with curves, with families of curves, is also right. The global space can be realized as a coarse moduli space or not. So I want to understand what is missing.
So what is missing here is the schemeness of the base, because I chose the base to be a moduli stack of quasipolarized surfaces. And there are some results about the stack being Artin, and probably there are some results about this stack admitting a moduli scheme of some sort. But like I didn't know enough geometry to assume that it is a scheme.
But so if you restrict yourself to polarize,
Yes.
then you get a coarse moduli space, a projective variety at the end, or I mean, not necessarily projective, but you know, or not.
So point-wise, I will get.
No, not point-wise. If the base, right, say you take out, right. I mean, you only allow polarized K3s.
Mm-hmm.
Yeah, forget about the quasi-polarization. Then you still don't get a coarse moduli space at the end of the day, or do you?
I believe that I do.
Okay.
No, maybe you're right. Maybe not. So
Yeah.
if
I don't think.
if
I don't know.
if there are results that's like your coarse moduli space exists, I believe that this construction should give the same result. But a priori, I'm not sure how to do.
I think over the polarized locus, there's not a where you actually have a polarization, not a quasi-polarization, then it's fine. You have a coarse moduli space. It's okay. But I think the whole point of your construction, you want to extend it over the quasi-polarized. So that's, but yeah, I mean, if you just stick to the polarized, it's fine.
And finally, I can observe that M goes to K is fiberwise a scheme. And in a couple of words, M being a colimit in stacks can be constructed as the stackification of the colimit in pre-stacks. And stackification, just like fancy for level 2 sheavification, it does not change geometric fibers. So in this construction, we see that geometric fibers are good moduli spaces fiber-wise. And therefore, over the ample locus, we have that fiber-wise, we get a scheme, like the good moduli space, or like the moduli space of stable sheaves, classically. And over the quasipolarized locus, I use the assumption that stability is equivalent to semi-stability to show that I can move away, that I can vary the quasipolarization a bit to make it ample, and the moduli space remains the same. And then I use the classical theory then. Without changing moduli, without changing the moduli problem. Okay. Do I have 10 minutes to find the strange duality morphism in the relative setting, or is the seminar 50 minutes?
You have 8 more minutes.
8 minutes, okay. I think it might be enough. So the strange duality morphism in moduli, in this setting, we replace a point with the moduli stack of surfaces. And we replace cohomology with push forwards. And let us consider the following picture. Okay, the stack of quasipolarized K3 surfaces. It has the universal K3 surface, which is also a stack. And we constructed the moduli stack of stable sheaves, which is pointwise scheme, but there is a problem with this step. Namely, it does not have a universal sheaf. Over the ample locus, solving this can be done by taking a cover of MV with some quotient of a with some code scheme, and quotienting out by a reductive group recovers MV. But in the quasi-polarized case, I couldn't retrace these boundedness conditions to construct the code scheme, so I took the moduli stack of stable sheaves, the UV, where I still remember the automorphisms of sheaves. And then further, I am not satisfied enough with working over, because the universal K3 surface does not have the algebraic point class. So let us recall, if X was a surface over a point, we consider K-theory vectors of rank, determinant, and some points. And we need them to live in the algebraic K-theory of X in order to be able to apply the Fourier-Mukai transform. And in order to recover points, to add points to the picture, Alina and Dragos came up with this improvement of considering Y, which is X cross X over K. Or you can also think of it as follows. X can be viewed as the stack of pointed quasi-polarized K3 surfaces. And then Y is the universal pointed K3 surface. And this map admits a section class, which will represent the point class. Maybe I write it as star. And then we can choose vectors. The form V is equal to rank some fixed determinant, which is a power of quasi-polarization, and some number of points. So in order to not do all the same constructions from the previous section for X, I can take pullback and denote the pullbacks like this. In order to construct theta line bundles, I again take the product of RV with our universal pointed surface. This is the product over X, because we traded points for the moduli step. And keeping the notation P1 and P2 from the introduction, I define for V and W on Y, which are orthogonal. I define LW on RV as the determinant of the push forward of the universal sheaf E on RV cross W, tensor the pullback of the class W. And it will be a line bundle on RV. We'll have this line bundle L W on RV. We observed that this arrow from RV to NV is a good morphism. Therefore, it satisfies descent. And using orthogonality of V and W, I can write a co-cycle condition for LW with respect to this good morphism. And therefore, LW descends to NV. And I also denoted by LW. And in order to descend it further to MV, one would want to check that the restriction of LW to every point of to every fiber of the vertical map is isomorphic to the fixed degree of a polarization, of the quasipolarization, which Alina and Dragos did. And therefore, by the simple version of the seesaw lemma, LW descends further to MV, and this theta W is called the theta line bundle. And this is probably the most interesting and involved part of constructing the strange duality morphism. And then we're basically retracing the classical definition. We have theta W on MV and theta V on MW. And we have the product of these moduli stacks over K. And by defining the divisor locus, again, by the condition of jumping zeroth cohomology, we get a certain line bundle of T, which is isomorphic to the box product of theta W of theta V. And pushing theta W and theta V to K would result into vector bundles W and V. And in a similar fashion, a section of O of T produces morphism from the structure sheaf of K to W tensor V up to a twist by a line bundle. And therefore we get the morphism D between the line bundle between the dual of W and V, also up to a twist. And this is called the strange duality morphism. And proving the generic strange duality in this case is, I believe, a formal repetition of Alina's paper. I think I'm ready to stop here because I don't want to tire people out.
Okay, great.